Imagine for a second that you're tasked with rebuilding a complex three-dimensional reality.
Right, like an intricate molecule or maybe a map of a bustling city.
Exactly. But there's a massive catch. 99% of the object is totally invisible.
Wow.
Yeah. All you have to work with are a few random distance measurements between hidden points. So if you've ever felt like you're trying to put together a puzzle with missing pieces, wait until you hear how mathematicians do it.
And, what's fascinating here is that this isn't just some abstract math puzzle. This is the exact geometry of incomplete information that powers everything from GPS sensor networks to cutting edge drug discovery.
Which is wild.
It really is. I mean, when you only have a tiny fraction of the data, the stakes of how you reconstruct the rest are incredibly high.
And to figure out how this actually works, we're jumping into a stack of seriously impressive sources for today's deep dive.
Hmm.
We're looking at a pretty dense mathematical survey from the 2014 SIAM Review by Leo Liberty and his colleagues, and we're pairing that alongside a modern presentation literally titled Reconstructing Reality from the Void.
That is quite the title.
It's intense, right? So our mission today is to explore the Euclidean distance geometry problem, or the DGP, and really understand how mathematicians basically fold the invisible and recreate reality out of thin air.
Yeah, and to solve this mystery of missing reality, we first have to, map out the clues we actually do have.
Right.
We organize these clues using a fundamental structure called the Euclidean distance matrix, or the EDM.
The EDM. Okay, so the DGP essentially asks if we can assign exact spatial coordinates to points given only their pairwise distances.
Right, just the distances between them.
But because data in the real world is profoundly sparse, figuring out how to complete this matrix, the EDM completion problem is what computer scientists call strictly NP hard.
Yeah, which is just a technical way of saying it is a notoriously brutal computational challenge.
Okay, let's unpack this. The matrix itself has a very specific anatomy, right?
It does. It's governed by a few strict, completely non-negotiable rules.
Mm-hmm.
First, there's the hollow diagonal.
The hollow diagonal.
Yeah, meaning the distance from any point to itself is always zero. So the main diagonal running straight through the matrix is just, a line of zeros.
Which makes sense. I am 0 inches away from myself.
Exactly. And second, we have symmetric reflection. The distance from point A to point B is the exact same as B to A.
So the distance from my house to yours is the same as your house to mine. That's basic table stakes. But the sources point out a third rule, the low rank bound, and that seems to be the actual heavy lifter here.
Oh, absolutely. The low rank bound is the absolute constraint of this entire geometry. In a given dimension, let's call it K, the matrix rank is exactly the minimum of either the number of points, n, or K plus 2.
Wait, okay. What does rank actually mean in this context?
Yeah.
Let's say I have a massive matrix of distances between, 1,000 different points in a 3D space.
Okay.
It's 1,000 by 1,000 grid of numbers.
Right. But even with 1,000,000 data points, if those points exist in physical three-dimensional space, the mathematical rank, basically the fundamental dimensionality of that matrix is capped.
Capped at what?
Well, for 3D space, K is 3, so K plus 2 is 5.
Oh, wow.
Yeah. No matter how massive the matrix is, all that overlapping distance data collapses down to a maximum rank of 5.
That's crazy.
It's a rigid mathematical constraint. It's what keeps the geometry anchored in physical reality rather than letting the numbers just, spin off into infinite abstract dimensions.
This sounds exactly like a spatial game of Sudoku.
That's a great way to put it.
You have a grid, a few numbers filled in, and strict rules about what can go in the blanks. But wait, in Sudoku, I just need to find a number 1 through 9.
Right.
Here, aren't we looking for points floating anywhere in infinite 3D space? I mean, distances alone just float freely.
They do.
If I say 2 points are 5 feet apart, they could be anywhere, oriented in any direction. How is a matrix of distances enough to pin down a real physical location?
Well, that's the thing. Distances floating in a void are totally useless on their own. To anchor them, to turn those relational distances into a fixed coordinate system, we need a mathematical bridge.
And according to our sources, that bridge is called the Graham matrix.
Yes.
So we're moving from the problem, the free-floating distances, to the theoretical solution.
Exactly. The Graham matrix bridge is built using an equation known as the polarization identity.
Okay.
It looks roughly like this. Gij equals 1/2 times the quantity of d0i squared plus d0j squared minus dij squared,
Hold on, that sounds like a massive alphabet soup of variables. What is the actual mechanism there? Like, what is the math doing?
It's pure magic, honestly. It takes purely relational distances and transforms them into precise angles, usually denoted by theta and norms radiating from a fixed origin point.
An origin point.
Right. And by decomposing this resulting gram matrix, we can extract the exact physical coordinates of our points.
Wait, hold on. If I tell you the distance between my coffee cup and my microphone, that doesn't tell you the angle between them?
No, it doesn't.
If I just measure a length, are you saying the math just manufactures angles out of thin air?
If we connect this to the bigger picture, the math isn't manufacturing angles, it's forcing them.
Forcing them how?
Notice the zeros in that equation I mentioned, the D0I and D0J.
Right.
That zero represents a fixed central origin point. The equation isn't just looking at the distance between your coffee cup and your mic.
Oh, I see.
It's triangulating the distance from the origin to the cup, the origin to the mic, and the cup to the mic.
So it's creating a rigid triangle.
Exactly. And when you lock down all three sides of a triangle, the geometry becomes so constrained that only one specific angle can physically exist between those points.
Wow.
Because we anchor everything to that fixed 0 point, the overlapping distances restrict the geometry. The gram matrix reveals the angles that were secretly hiding inside those distances all along.
Okay, so we have the theoretical bridge, but how do algorithms actually cross it when the starting data is mostly blank?
That is the million-dollar question.
Right, because if we don't have enough distances to form those rigid triangles, the gram matrix has nothing to work with.
Exactly.
And our sources outline two incredibly different paths for dealing with the void: heuristics versus non-convex optimization.
Right, two completely different philosophies for filling in the blanks. Let's look at path 1 first, the isomap family.
The heuristic approach.
Yeah, it treats the known distances as a network or a graph. It uses a classic algorithm called Floyd-Warshall to literally walk the shortest paths between connected points.
So it's estimating.
Yes, it estimates the missing long distances by hopping node to node. Once the matrix is filled with these hop-by-hop estimates, it uses principal component analysis, or PCA, to project everything into the final spatial dimensions.
Wait, if isomap is just blindly walking between the points we do have to guess the distances we don't have, that assumes the space between them is completely flat, right?
Oh, entirely flat, yes.
What if there's a massive hole in the data? Like if I'm trying to estimate the distance from New York to London, but I only have data points tracing up through Greenland and Iceland.
Isomap is going to trace that massive curve and just assume it's a straight line.
Which is completely wrong.
Right. And that is the exact vulnerability of the heuristic approach. Look, Isomap is computationally light. It's extremely fast.
Sure.
It is fantastic for massive data sets where you have highly abundant raw data and just a few missing gaps. But it's mathematically approximate. There are no theoretical guarantees.
So if your initial data is profoundly sparse, those shortest path estimates become wildly inaccurate.
They do. They bend and distort the final reality completely.
Here's where it gets really interesting. That brings us to path 2, matrix RRLS,
Yes.
which stands for iteratively reweighted least squares. This is a heavy optimization approach, right?
The heavy hitter, yeah.
Instead of guessing distances node by node, it treats the missing data as a non-convex rank minimization problem.
A mouthful, I know.
Yeah, the sources say it minimizes a, quote, smoothed log determinant objective, unquote. What is the actual mechanism there?
Think of matrix RLS like shrink wrapping an irregularly shaped object.
Okay, I can picture that.
When you first throw the plastic over the object, it's baggy, it's loose, it's chaotic. That baggy plastic is your high rank noise. It's the matrix filled with missing, unconstrained data.
Got it.
Then, the algorithm introduces a smoothing parameter, usually called epsilon.
So epsilon is the heat gun.
Yes, perfect. As the algorithm iterates, it slowly shrinks that epsilon value. The heat is applied.
Okay.
As epsilon shrinks, it forces that chaotic, high-dimensional noise to collapse. It conforms tightly to the underlying low-rank true geometry of the object.
Oh, wow.
It actively penalizes the matrix for trying to exist in higher dimensions, literally squeezing the math until it flattens into the correct 3D shape.
But the Science Review paper mentions that standard matrix completion theory actually falls apart here.
It does.
Because usually, matrix completion relies on the measurement basis being orthonormal, right?
Yeah.
Meaning all the axes are perfectly at right angles, totally independent of each other.
Right, which in distance geometry, they absolutely aren't.
Exactly. So how does matrix RLS shrink wrap this data without getting stuck in, like, chaotic mathematical loops?
It creates a localized safe zone which mathematicians call a tangent space
The
basin.
tangent space basin.
Yeah, because the overall mathematical landscape is non-convex, meaning it's full of chaotic hills and valleys where an algorithm can easily get trapped in a local minimum.
A local minimum being a spot that looks like a solution but isn't.
Exactly. To avoid that, matrix RLS establishes a restricted isometry property, or RAP.
An RIP is basically a rule that says within this specific restricted area, distances are preserved and the math behaves predictably.
You nailed it. It restricts that property specifically to the tangent space of the matrix. If the algorithm can start its shrink wrapping process inside this smooth, predictable basin, it completely avoids all those chaotic traps outside of it.
That's incredibly clever.
It really is.
Yeah.
By staying in the basin, it guarantees what we call local quadratic convergence,
Which
means a rapid, direct slide down into the exact, mathematically perfect ground truth geometry.
Okay, so isomap is like asking a local for a shortcut. It's fast, it assumes a lot, and it's usually good enough if the city is well mapped.
Right.
But matrix IRLS is like a supercomputer simulating gravity. It's heavy, it's slow, but it forces all the chaotic, noisy data to collapse into the exact true shape of reality.
Exactly. Matrix RLS is designed for scenarios where measurements are profoundly scarce or just incredibly expensive to obtain.
Yeah.
And it thrives on severely ill-conditioned data.
Yeah, the sources highlight data with a condition number of 10 to the fifth power, which is huge.
A high condition number just means the problem is mathematically fragile.
Okay.
The final output is intensely sensitive to even microscopic errors in the initial data. If you use standard optimization methods on data with a condition number that high, the algorithms completely collapse. The errors just compound too fast.
Right.
So matrix RLS pays a higher computational cost, but it navigates that fragility perfectly to extract the true geometry from the absolute theoretical minimum of data.
So matrix IRLS is willing to burn massive compute power to squeeze truth out of practically zero data.
Absolutely.
But who actually needs that level of precision? Like, where is data so incredibly expensive that we'll pay any computational price for it?
Human biology.
Biology, which leads us directly to the molecular distance geometry problem, or MDGP.
Right. Here we're trying to figure out the 3D structure of a protein.
Because proteins are the building blocks of life.
They are. And whether a protein cures a disease or causes one is entirely dictated by its physical 3D shape, how it folds.
Right.
But we can't just put a protein under a standard microscope and snap a photograph. We have to use nuclear magnetic resonance, or NMR, to deduce its shape.
But NMR data is painfully sparse, right?
Incredibly sparse.
It only gives us a tiny fraction of the distances between atoms, usually just the ones that are very close together.
Right.
The sources feature test instances of this, like reconstructing the two-oral protein backbone and a protein called 1-BPM.
And this is where we see the sheer miracle of matrix RLS in action. The algorithm reconstructed the exact geometry of protein 1-BPM.
Wow.
And to verify that it actually worked, the researchers had to align their reconstructed molecule to the known ground truth model of 1-BPM.
Okay.
They used something called an orthogonal Procrustes transformation.
Okay, wait. I know Procrustes is from Greek mythology, the blacksmith who stretched or cut off people's legs to make them fit his iron bed.
Yeah, it's a bit grim.
Right. So what is an orthogonal Procrustes transformation doing to a protein?
Well, it's just a method of comparing two shapes. When matrix RLS reconstructs a protein from relational distances, it might build a mathematically perfect model, but the model might be floating upside down or facing backward relative to the reference database.
Oh, I see.
So the Procrustes transformation mathematically rotates and reflects the reconstructed molecule crucially without distorting or stretching it to see if it perfectly overlaps with the ground truth.
Like fitting a key into a lock to see if the teeth align.
That's a perfect analogy.
And when they ran that alignment,
The result was a perfect structural overlap.
incredible.
Matrix RLS mapped the entire complex structure of the protein using merely around 0.5% of all possible pairwise distances.
Wait, really? Half of 1% of the data to rebuild the entire physical reality.
Yes.
That is staggering. But the Siam review paper also outlines a completely different approach for the NDGP, right?
It does.
Instead of using continuous optimization like matrix IRLS, it uses the chemical rules of the atoms themselves. It's a concept called discretizability and the branch and prune algorithm.
Right. Because normally, trying to solve this by placing atoms in 3D space is a continuous nightmare. There's an uncountable infinity of possible locations for every single atom.
Right. They could be anywhere.
But we have a biological cheat code, the rigid geometry hypothesis.
Okay.
Because of the laws of chemistry, we already know the exact lengths of covalent bonds, and we know the exact angles between bonded atoms. This natural atomic ordering takes the infinite possibilities and severely restricts them.
And that restriction leads to the rule of spheres, which, frankly, absolutely blew my mind.
It's so cool.
If you intercept K spheres in K dimensional space, for example, intersecting 3 spheres in 3D space, they don't intersect in an infinite number of places.
Yep.
With probability 1, they intersect in exactly 2 points.
Think about the physical geometry of it. One sphere is a hollow globe. When you intersect it with a second sphere, the overlap forms a perfect circle.
Right.
Now introduce a third sphere and intersect it with that circle. A sphere passing through a circle will only pierce the circle's edge at 2 exact distinct points.
Which fundamentally changes the math. It turns an infinite, uncountable search space into a simple, binary choice. The atom can only exist at point A or point B.
Exactly. And that allows for algorithm 1, the branch and prune algorithm.
Okay.
It creates a binary tree of possibilities. Instead of searching infinite space, you just choose between position 0 or position 1 for the next atom.
So instead of trying to map a galaxy of infinite locations, branch and prune turns protein folding into like a cosmic game of Plinko.
Yes.
The atom drops, and it can only bounce left or right, and it goes down the board, branching out. But what happens when a drop hits one of our known NMR distances?
Well, that known distance acts as a pruning edge.
A pruning edge.
Right. If the atom bounces left into a position that would place it 10 angstroms away from another atom, but our sparse NMR data tells us they absolutely must be 4 angstroms apart.
That path is chemically impossible.
Exactly. You prune that branch, you chop it off the tree entirely.
So the algorithm just abandons that entire timeline of possibilities and only follows the branches that perfectly match the sparse data we have.
Yes. But this raises an important question. What happens when you run this all the way to the end?
Okay.
Matrix RLS forces the chaotic data to shrink wrap down into one exact answer.
Mm-hmm.
But the branch and prune algorithm is unique because it doesn't just find one answer. It finds all mathematically valid realizations.
Meaning it finds every possible way that protein could fold without breaking the laws of physics or violating the NMR data.
Exactly. It finds all the hidden isomers of the molecule.
Yeah.
It maps every mathematically possible reality that fits the clues.
So what does this all mean? For you listening, why should you care about Gram matrices, shrink wrapping algorithms, and pruning edges?
Right.
Because these equations take the void of missing information and weave it into tangible reality.
Yeah.
We see this with systems like AlphaFold predicting life-saving drug targets,
Mm.
or a cluster of wireless sensors trying to locate themselves in a collapsed building where GPS doesn't reach. The math is the same.
It is.
And the choice of how to fold that invisible reality, whether you use a fast heuristic shortcut like ISOMAP, or a heavy, uncompromising optimization like Matrix RLS, is entirely dictated by your sensor budget.
Exactly.
How much data do you actually have, and how much computational fire are you willing to burn to find the truth?
And we just saw that Matrix RLS can perfectly reconstruct a physical protein using just 0.5% of the data.
Mm.
That's for physical space. But what about abstract spaces?
What do you mean?
Well, if algorithms can reconstruct physical reality from 99.5% missing data, imagine what happens when we apply distance geometry to our social networks, our internet search histories, or our psychological profiles.
Oh, wow.
How much of you is truly hidden if an algorithm only needs 0.5% of your distances to map your entire reality?
That is a thought that is going to keep me up at night. Next time you think you've hidden the pieces of your own puzzle, remember how little mathematicians actually need to see the whole picture? Keep exploring the invisible structures all around you.